Okay, so for the final section of this chapter on reinforcement learning, I'd like to talk about AlphaGo, test time compute, and expert iteration. Although the reinforcement learning on large language models does not directly utilize these ideas, there are close, important conceptual connections. To talk about AlphaGo, let's start with two-player zero-sum games. So in a two-player zero-sum game, two players compete against each other, and one player's reward is precisely the loss of the other player. So if one player wins, well, then the other player loses. In a simultaneous move game, the two players make their moves simultaneously. So in a game of rock, paper, scissors, as an example, the two players offers their move simultaneously, and the winner is determined. On the other hand, in a sequential move game, also referred to as a turn-based game, the two players make their moves in turns. So the game of chess and in the game of Go, two players make their moves in an alternating fashion. However, we will think of these sequential move games as simultaneous move games where the two players each offer their individual policies, pi1 and pi2, at the start of the game. Now, if you think about it, this is not that uh, uh, unrealistic because in a real life competition of games, two humans show up to the board and they offer their brain. They offer themselves as the agent that plays the game. So the humans themselves are the policies pi1 and pi2. These policies, they can strategize, they can adapt to the opponent's moves, etc. And they can also make randomized decisions if that is considered, if the policy considers that to be a good choice. In minimax optimization, as opposed to, let's say, minimization or maximization optimization, we minimize with respect to one variable and maximize with respect to another variable. So here in this minimax optimization problem, agent one aims to maximize this reward, and then agent two aims to minimize this reward. The interpretation in a zero-sum game is that R1 represents the reward of player one. So player one wants to maximize the reward, and player two wants to minimize the reward of player one because that's the same thing as maximizing its own reward. We say a configuration for these two players is a solution to the minimax problem if it is a Nash equilibrium. So this is the definition of the Nash equilibrium. So to give an interpretation, if we are at the configuration theta 1 star, theta 2 star, if player one unilaterally changes its move and deviates from theta 1 star, then that only serves to reduce the reward, which is undesirable because player one aims to maximize its reward. On the other hand, if player two unilaterally changes its configuration to theta 2, well, then that only serves to increase the reward, which is undesirable because player two wishes to decrease the value of R. The standard reinforcement learning is posed as a maximization problem. We want to maximize the expected cumulative discounted return. However, when you have more than one agent, well, when you have an adversarial training and two-player zero-sum games, these are posed as minimax optimization problems. As an example, let's look at the game of rock, paper, scissors. So in a game of rock, paper, scissors, the players employ randomized strategies, a probability theta 1, a p theta 1, p theta 2, and there's an expected payoff. So there's no need to look at sort of this in detail, but the point is that player 2 offers as its strategy a distribution on rock, paper, and scissors. And the same is done for player 1. Player 1 offers a distribution on rock, paper, and scissors. And rock beats scissors, scissors beat paper, and paper beats rock, right? And rock and rock results in a tie, scissors and scissors results in a tie. So that's what this payoff matrix is representing. Of course, this is a toy example, but we want to relate this to deep learning with multiple agents. So let's consider p theta to be a parameterized distribution where it's parameterized by parameters theta 1, theta 2, and theta 3, and it is fed through a softmax normalization layer so that p1 ends up representing a probability distribution. And the same with p2. So p2 is parameterized by these theta 2 values, but it's fed through a softmax distribution to become a bona fide probability distribution. Now we know that the Nash equilibrium for rock, paper, scissors occurs when the player offers rock, paper, and scissors with equal 1/3 probability. If a player has a bias towards any of the three moves, then that can be exploited by the other player, and that would not be a Nash equilibrium. So then how do you solve minimax optimization problems? Well, in deep learning, we solve everything with first order methods using stochastic gradients. So things like ADAM and SGD, these are the things that we use to perform any kind of optimization problem, not minimization optimization, maximization optimization, and also minimax optimization as well. But if you want to analyze the convergence of minimax optimization, or if you don't care about the analysis, but you just want your minimax optimization to empirically converge, this is something that's quite tricky. The convergence of minimax optimization should not be taken for granted. And in practice, a lot of delicate care is needed compared to solving minimization optimization. The training of GANs, for example, so the GAN is the abbreviation of generative adversarial networks. This involves a minimax optimization formulation. So, and the training of GANs is famously tricky to stabilize. And in the following slides, I'll show some plots indicating that even the minimax training of rock, paper, scissors game, this really simple toy example, is actually can be a highly unstable process. Reinforcement learning training is already more unstable than supervised learning. People say that supervised learning is stable, reinforcement learning is much more harder to stabilize. And often people have the idea that you want to convert as much of reinforcement learning, as much of the components of reinforcement learning into a manner that resembles supervised learning in order to stabilize things. When you do multi-agent RL, so two-agent RL in the case of two-player zero-sum games, the training and the stability becomes even more delicate than non-reinforcement learning minimax training. So two-player minimax reinforcement learning is something that can be very tricky to pull off. So what are the algorithms that we can use to solve minimax optimization? Well, a very simple algorithm one might try is simultaneous gradient descent ascent or gradient ascent descent. So here's the specification of the algorithm. So for theta 1, we want to do a gradient ascent with respect to the loss function. So we take the derivative with respect to the first variable, we perform gradient ascent. And then for the second variable, for the second agent, we want to perform gradient descent. So we differentiate with respect to the second variable, and we perform gradient descent. This is referred to as simultaneous gradient ascent descent because the ascent step and the descent step are performed in parallel. So that's why it is referred to as simultaneous. This is one of the simplest minimax optimization algorithms, but this can fail to converge on even very simple examples. So even on this rock, paper, scissors example, we can observe that the dynamics doesn't converge. So here I implemented and ran this simultaneous gradient descent ascent on this toy example. And we initialize the probability distributions for player 1 and player 2 to be non-uniform. So as you can see, the probabilities are not all uniformly 1/3. They're not uniformly all 1/3 at the beginning. And we would hope through training that player 1 and player 2 will converge to the Nash equilibrium, namely having 1/3 probability for all three moves. But that's not the case. We see that the probabilities oscillate for both player 1 and player 2, and the amplitude of oscillation grows as the iterations progress. Now, why does this happen? Well, minimax optimization can fail. So one failure mode of minimax optimization is these cycling dynamics. So and the cycling dynamics manifest in this example as players countering the other player. So let's say player has a large probability of playing rock. Player 2 counters that by playing paper. And then observing this, player 1 counters this by playing scissors. And then observing this, player 2 counters this by playing rock. And this process just goes on and it amplifies. And when there's no mechanism to dampen this cycling behavior, it just grows and the training becomes unstable as shown in these plots. Okay, so how do we fix this? Well, one approach is called the extra gradient method. So for the extra gradient method, imagine you and your opponent make regular one-step updates, then you evaluate the gradient from there, and then you use that gradient to commit to the update. Actually, there's a sign error. This should be plus. This should be minus. This should be plus, and this should be minus. Okay, so let's read through the algorithm. So player 1 wants to maximize its reward, so it'll perform gradient ascent, and then player 2 will perform gradient descent because player 2 wants to reduce the reward. But actually, player 1 and player 2 are not going to commit to this update. They're going to imagine themselves and the opponent making this update. And then from there, the player will evaluate the gradient from there. And then by evaluating the gradient from there, player one performs gradient ascent from this point. So not from theta one temp, it will go back to original point, but it will use the gradient evaluated at this updated point and perform the gradient ascent. For player two as well, player two will perform the update from theta two, but it will evaluate the gradient at the single step update points and then perform gradient descent. So this is roughly speaking the agents looking ahead. So imagining what I would do, imagining what the opponent would do, and then performing updates based on that one step sort of look ahead argument. And this is closely related to the idea of learning with opponent level awareness, referred to as LOLA. If you look at these convergence plots for this extra gradient method, the extra gradient method does converge for these two-player zero-sum games. So we initialize the player one and player two strategies in some way, and they do still see this oscillations, but we can observe that the distributions, they converge to the uniform one-third probabilities, which is the Nash equilibrium. Another remedy of this unstable mechanism is the so-called use of the anchoring or the weight decay. So if we read through the algorithm, this is basically the same as simultaneous gradient ascent descent, but we have this weight decay mechanism. And with this weight decay mechanism, as you can see in these plots, the convergence is very stable and it's also quite efficient. A generalized version of this anchoring mechanism where you perform weight decay not necessarily towards zero, but to any arbitrary point, that's referred to as anchoring, and it is something that I've done research on in some of my prior work. Okay, so the takeaway is that to solve these two-player zero-sum games, you should not use simultaneous gradient ascent descent, but you can do something like the extra gradient method, like LOLA, or you can do weight decay to stabilize the trading dynamics. But there's one more crucial structure in the game of chess and Go, and that is that the game is symmetric or anti-symmetric. So we say that a two-player zero-sum game has an anti-symmetric payoff if when you change the moves of player two and player one, that results in the equal but opposite reward. When the two-player zero-sum game has this kind of symmetry or anti-symmetry, then the Nash equilibrium is attained at some input where the two players play the same move and the reward is equal to zero. And there's a typo here, so I should remove these subscripts so that the inputs are the same. So when the reward has this anti-symmetric structure, then the gradient with respect to the first input is the same as the gradient with respect to the second input, provided that the two inputs are the same. So therefore, if you initialize the two players' moves, theta 1 and theta 2, to be equal at the beginning, then the algorithm SimGDA, simultaneous gradient descent ascent, actually simplifies in this way. Because of the symmetry, there's no need to keep track of the two different positions, the moves or the actions of agents 1 and 2. You can just combine them into one. But I just said that a simultaneous gradient ascent descent is maybe divergent, so you want to do the version of this with weight decay, and that simplifies in this manner. So the interpretation of this is that when you have a symmetric or an anti-symmetric payoff game, something like Go or chess, then you don't have to learn two agents. You can just learn one agent, and you can think of the agent player one playing against itself. So this algorithm can be interpreted as gradient ascent done on player one, with player one playing itself. So player two is a copy of player one. All right, so then let's talk about chess and Go. So chess and Go are two-player zero-sum perfect information games with anti-symmetric payoffs. So if you're not familiar with Go, but you're familiar with chess, or vice versa, conceptually, you can just think of them as basically the same type of games. They are two-player games. It's zero sum. They're zero sum because the loss of one player means the victory of the other player. It's perfect information because there's no hidden information. It's different from card games where the information is hidden from your opponent. Everything is on the board, so there's all the information is out there in the public, and we have the anti-symmetric payoff, meaning the rules are symmetric between the two players. Now, technically, these games are not perfectly anti-symmetric or symmetric because one player makes the first move. Now, if you want to be further technical, we can make the game symmetric if the first move is given to one of the players randomly. So if you randomize the first move, then the game does become symmetric in that regard. But because the game is mostly symmetric, we will train one agent to play both players. So we will only have one policy to play both black and white. Now, this contrast, so there are some board games where you have two players and the actions, the rules for the two players are highly asymmetric. If you have such a game, then it makes sense to train two policies for separately for the different players. But for chess and Go, the strategies for white and black are sufficiently similar, so it makes sense to train them as one single policy. So the board games chess, shogi, and Go, these are again two-player perfect information zero-sum turn-based games. For chess, the top human chess player was defeated in 1997 by the algorithm Deep Blue. The top human shogi player was defeated in 2017 by the algorithm Elno, and the top human Go player was defeated in 2016 by the algorithm AlphaGo. So in this lecture, I'll talk about AlphaGo and AlphaGo Zero. So these two algorithms, they combine search and learning to achieve superhuman play, initially in the game of Go, and later these algorithms were extended to the other board games, chess and shogi as well. These methods, AlphaGo and AlphaGo Zero, they represent landmark scientific accomplishments in artificial intelligence research, and they contain insights that are generalizable beyond the domain of games. Namely, AlphaGo and AlphaGo Zero crucially utilize this technique called MCTS. Now, the exact technique of MCTS, which I'll explain soon, this has not been successfully adapted to the setup of LLM reasoning or the reinforcement learning of large language models, but I think the algorithm MCTS has a lot of interesting and generalizable takeaways. So let's take a look at it. Okay, so next, let's go through the AlphaGo training pipeline. So for the first step of training AlphaGo, we perform imitation learning. We instantiate a policy network pi theta, and this is a neural network, which we refer to as the policy network. It takes in as input the state of the Go board, and then it produces a probability distribution on the next actions that we should take. And this is trained from expert play record. So Go is a game with a lot of history and a lot of professional matches. And these professional matches are documented. So you have a record of which moves were played in the precise order in which they were played. So from that, we can construct a data set. The data set has a board position S, and then it also comes with the next move that the professional Go player, the expert, has played in the past. So we train the policy network to predict the expert player's next move using some sort of cross-entropy loss. The specific architecture that was used in the AlphaGo paper is something like a 13-layer convolutional neural network. This step by itself is already pretty good. So if you train the policy network with a neural network based on the expert play record, this can beat many human players, but it's still not yet powerful enough to beat the expert human players. Okay, so then in step 2 of the AlphaGo training, we perform reinforcement learning through self-play. So as the first step of this stage, we initialize a reinforcement learning agent to be equal to the imitation learning agent. So in step 1, we did imitation learning, and we use this as the starting point of our now self-play reinforcement learning. And then in the next step, we have the current policy play against itself, but actually it has to play not its current self, but a slightly earlier version of the parameter of the agent. And this is done for stability reasons. So by having sort of this delay mechanism where the opponent is a slightly weaker version, an earlier version of your current policy, this has the effect of stabilizing training. For the sake of notation, let's write Z to indicate whether the first player has won. So if Z is +1, the first player has won. If Z is -1, then the first player has lost. Then we have the agent play against itself or an earlier version of itself, and we perform an undiscounted policy gradient update. Because the game has an anti-symmetric payoff, we don't keep track of two agents, we keep track of one agent. But to be precise, we keep track of one agent and an earlier version, but we can still think of it as a single agent. And we perform a gradient ascent on the first player playing against itself, and that leads to a policy gradient type update. So this reinforcement learning trained policy network has the same neural network architecture as the imitation learning network. Now this improves the agent. The agent is improved considerably. So the reinforcement learning agent beats the imitation learning agent by an 80% chance. So this is a significant improvement, but not a crushing improvement. The win rate is not something like 99%, but it is an improvement. Nevertheless, this reinforcement learning agent just trained using self-play, as this still cannot defeat human experts. Now, in principle, If the neural network is very large and self-play is done for very long, so if you expend a huge amount of compute, then we can expect the reinforcement learning agent to, at some point, converge to perfection and also beat all expert human players. But under these practical compute constraints, the reinforcement learning agent was not able to defeat the top human experts, so we need something more to be able to do that. Okay, so this leads to the third stage of the AlphaGo training. So what we do is we train a value network. The value network is meant to approximate the value function of the current RL policy, which we kind of hope is sufficiently close to the optimal value function. And to do this, we use the standard Monte Carlo policy evaluation method. So what we do is we have self-play with the strongest policy that we have so far to collect S comma Z pairs, where S is the current board state and Z is whether the current player goes on to eventually win or lose. Now, given a current state, if the player one eventually goes on to win the game, then that probably means this current state, the current board state, is an advantageous state. If there's a current state and the first player eventually goes on to lose the game, then that probably means that the current board state is a disadvantageous board state. With this data, we perform stochastic gradient ascent in the usual Monte Carlo policy evaluation manner. So we learned the v value function, but what about the q value function? Well, the q value function is also useful. It's actually needed later in the MCTS stage. But in this game, the dynamics is deterministic. If from the current state, if I choose to place a move somewhere, there's no randomness in the outcome. If I choose to place a move somewhere, that's where the move will be placed. So because the dynamics in this environment is deterministic, the Q function is actually equal to the V function in terms of the information it contains. So it's enough for us to just learn the V function. So there is a minor technicality when it comes to the sign here. So if I'm player one and I observe a current board state and I make a move, then the turn goes to player two. Now, when player two observes the strength of the board, player two has the equal but opposite consideration as I do. So if the board is advantageous to me, that's disadvantageous to player two and vice versa. So when you relate the Q function and the V function, you need to take into account this sign difference because the moves are going back and forth between player one and player two. Another minor component of the AlphaGo training is in the step 4. We need to train a fast rollout policy to do fast rollouts. I'll explain what rollouts are, but this fast rollout policy is trained via also imitation learning. So this is a much more lightweight architecture. It has much fewer parameters, much fewer computation is required to evaluate this fast policy compared to the imitation learning policy or the reinforcement learning policy. In comparison, in the AlphaGo paper, they report that the fast policy required 2 microseconds to evaluate, whereas the reinforcement learning policy required 3 milliseconds to evaluate. So that's a 1000x difference in terms of compute time in evaluating these policies. Now, this fast policy, trained via imitation learning, it's not a good policy. It cannot beat reasonably good human beings. It's much weaker than the imitation learning or reinforcement learning policies, but it does understand the most basic principles of the game. So the most obvious things this fast policy does understand. Okay, so at this point, we have 2 options for a neural network only play. Option 1 is to simply use the reinforcement learning trained policy. Option 2 is, since we've trained the V value network, which equivalently gives us access to an approximation of the Q function, we can play a greedy policy with respect to our learned Q function. And in principle, either of these approaches should work. So the use of these raw neural networks could beat a human, could beat the expert human players if we had an exorbitant amount of compute. And it's also actually possible to estimate how much compute this would actually require. However, under practical compute constraints, this pure neural network play is not enough to beat the expert human players. So we need one more component. And the component that we need is a tree search mechanism. Let's start with a pure tree search mechanism. So in a pure tree search, We consider all possible future board states that could possibly be played. This approach is also called Minimax tree search, since I try to maximize my reward while my opponent tries to minimize my reward, because of course it's a zero-sum two-player game. At every board state, the optimal action is chosen by maximizing the optimal Q function. Now, a priori, this might not seem like a useful formula because without any learning, I won't know the optimal v values function for most states, or the Q value function for that matter. But it turns out that, well, if we're at a terminal state, if we're at a state where the game is 1, then we actually do know the optimal v value function because I won, so the reward is 1, or I lost, so the reward is -1. So at the end of the game, the v value function value is known if you just know the rules, merely know the rules of the game. So what you can do is once you expand this tree, this imaginary tree of enormous size, you expand it to all possible game scenarios and you reach the end game states. Well, once the game ends, you know what the v value function is, then you can recursively backtrack using an idea, well, using like a dynamic programming mechanism to find moves that take you to a winning board state. This pure tree search based method does not require any learning. It just requires knowledge of the game rules. The problem, however, is that this is not implementable because this strategy is infeasible because for moderately sized board games, the size of the tree and therefore the computation size just exponentially blows up. And it's just not possible for, even with an advanced computer with all these GPUs, it's not possible to consider all possible chess scenarios. At this point, let's think about how humans play these kind of games because that's going to be instructive. Human players have intuition on a set of reasonable moves and how advantageous a board state is. And if we use the language of system one and system two reasoning, this intuition corresponds to system one thinking, and we can think of this as analogous to what a neural network learns. However, if you reflect on how you play these board games, you see a board state, and then you get a sense of what might be good moves, but you do not immediately act on these instincts. Instead, what you do is you sit there and deliberate through the future ramifications of the moves you make. So let's say you have 5 candidate moves that you think might be good. You sit there and you think of move number 1, and then you think, okay, if I make this move, the opponent will make that move, and then I do this, the opponent does that. You think through the consequences and see where this takes you. You do this for all of your candidate moves, and you choose the move that you think will lead to the best outcome based on this careful deliberation. And this deliberation corresponds to system 2 thinking, and it's analogous to something like a tree search. But if you again think about how humans do this deliberation, especially at the start of this chess game or the start of the Go game, the deliberation is not exhaustive. Let's say I want to assess the quality, the strength of this one move. Well, I imagine I make this move, but what move will the opponent make? Well, do you know exactly what move your opponent will make? Sometimes, but sometimes not. So there are several possible actions that your opponent can take. So you take those into consideration. But you cannot possibly consider all possible actions. So this corresponds to a limited width search. And then you go back and forth between the moves that you would make, the opponent might make several moves. You go think through this. And when you do this, you can maybe simulate 10 moves, 30 moves, many moves, but you will not be able to simulate this until the end of the game, because that would just take too much thinking, and we humans don't have the brain power to simulate from the start of a chess or Go game until the end of the game. What you actually do is you actually sit there and think about several moves, ahead, and you will conclude that if you make this move, you'll arrive at roughly this kind of board position. And at that, you will think, if I arrive at this kind of board position, that's going to be good or bad for me. So you don't simulate until the end of the game. You do a limited depth search. You deliberate and think that you'll get somewhere, and you'll make an assessment as to whether that somewhere is a good position or not. AlphaGo performs a neural guided search through what's called Monte Carlo tree search, MCTS. MCTS uses neural networks to guide and focus the search on the relevant regions of the game space in the same way that human deliberation works. Human deliberation has a limited width, it also has a limited depth, and the same is true for Monte Carlo tree search. So MCTS is the abbreviation of Monte Carlo tree search. It performs a neural guided search, selectively exploring parts of the tree based on the guidance of neural networks. And the first principle is that we gradually build up the tree, making it wider and deeper until we exhaust the given computational budget. A second principle of MCTS is that we control the width of the tree by only considering good actions. And this is exactly what we humans do when we think about these board games. You sit down at a position, you're given a position, you consider a handful of actions that you think may be good. You don't consider all actions exhaustively, you consider a handful of actions. And when you imagine you make a move, you imagine, well, the opponent making a move in response. And you might consider only one of the possible responses, or you might consider a handful of responses from your opponent, but you cannot possibly consider all possible actions as responses for the opponent. But which actions should you consider? For which actions should you focus your computational or your deliberative effort in planning these games? Well, you should only consider the good actions. So how are the good actions defined? Well, the good actions are defined in the MCTS for AlphaGo as actions that have a high probability on the imitation learning or reinforcement learning policies. Also, these are actions that score high on the Q function. And also, these are actions that we have not yet deliberated on. Okay, and here's the third principle of MCTS. So starting at your current board position, you consider a sequence of states based on the actions selected as previously described. And because we are doing a depth-limited search, we're going to arrive at what's called leaf nodes. These are board positions that take you somewhere, but this does not necessarily reach the end of the game. So in AlphaGo, the look ahead is about 30 moves or 60 plies deep. And this might be sufficient to take you to the end of the game if you're very close to the end of the game. But if you're in the beginning or the middle of the game, this will not take you to the end of the game. So after these 30 moves of look ahead or 60 plies look ahead, you arrive at a certain board state, which we denote as S tilde L. And we need to evaluate how good this board state is. Well, this is evaluated in two ways. The first approach is to evaluate this imagined board state, this look ahead board state, using the value network, which we hope is sufficiently close to the true value function. We also do rollouts. So starting at this intermediate board state, imagined board state, we do rollouts where we use the fast policy and we play out the game until the end. So this fast policy is not a good policy, but it understands the very basic principles of the game. So we have this just play out the game until the end and see who wins. And as a third approach, you do a combination of this first and second approach. So through this Monte Carlo tree search, we can get an understanding of how good this eventual look ahead board state S tilde L is. And if this is a good board state, then what we should do is we should commit to this next move. So currently, the board state that we're given is ST, and we have several options of actions, moves that we can make. And if S tilde L is a very good board state, then maybe we should choose the action to take us to the state S tilde T plus 1. So here's the high-level summary of MCTS. So we should consider moves based on intuition encoded in the policy networks or the Q function, and we use this to construct a look-ahead tree. We assess the strength of these leaf node positions by evaluating the value network on these imagined look-ahead positions, or by quickly playing out the game until the end using the fast policy. And based on the estimate of the value function at these leaf node positions, we backtrack and assign strengths to each actions at the root node, and we should commit to the best action AT after the deliberation. And by the way, in this MCTS algorithm, a common principle of planning and control is inaction. And this common principle is to plan for many steps ahead. Your planning should take into account many steps into the future, but you only commit to a single step. And that's what you do in board games, right? So you only make one single move each turn, but you think ahead, as many steps as possible when you think ahead, but you commit to one move. And then something happens in the next step. The opponent does something, You're given a new board state, and then you do the planning again. And again, in the subsequent turn, you will make one move, but you still plan ahead for multiple steps. This is a common principle in general, for planning and control, and it's also in action in the MCTS algorithm as well. Also, here's a quick slide on the biography of MCTS. So MCTS was successfully utilized in the AlphaGo paper. It was made quite prominent by the AlphaGo paper, but the MCTS of AlphaGo and a lot of the other components of AlphaGo is due to a lot of other prior work, which I outlined here in the slide. Okay, so is this MCTS thing good? I mean, it's certainly a bit complicated. So is this really necessary? I mean, why not just use pure RL? So here's a justification of this entire training pipeline. So first, if you don't do imitation learning, if you just do pure RL, then the reinforcement learning policy makes no progress. Because at the very beginning, if you randomly initialize your neural network to serve as a policy, the neural network will just make random moves. And those random moves will be very bad, and the reinforcement learning really doesn't make that much progress. And this is a common occurrence in reinforcement learning in general. Sometimes, in order to make reinforcement learning, you really need a good initial policy, and the initial policy must be provided in some way. In the case of Go, the initial policy is obtained by imitation learning based on the existing expert play record. Here is a figure that is taken from the AlphaGo paper, and it represents the ablation studies. So the ablation studies considers the subset of all the proposed components. And this study shows that in order to beat professional Go human player level, the rollout mechanism, the value network, the policy network, the entirety of this MCTS pipeline is needed. And if you remove any of them, then the performance significantly degrades. So this figure provides the answer to the question of whether this MCTS is needed. Yes, all of the components of the MCTS was needed in order to beat the top human player. So AlphaGo happened, the paper was published, and the algorithm was pitted against one of the top human players, and it defeated the top human player in a spectacular fashion. And it made an indelible impression on a lot of researchers' minds and also on the minds of the general public. But AlphaGo had some room for improvement. So one issue that the researchers of AlphaGo wanted to resolve is, can we eliminate the reliance on imitation learning on expert play data? Because yes, I mean, for the game of Go, the imitation learning data, the expert play data is present, so there's not a problem for using it. But maybe in other domains, there might be domains where expert data is not available or would be very expensive to acquire. The victory of AI over humans feels a little bit imperfect if the AI was trained on the human data. There were also some obvious technical improvements that could be applied. So the neural network architecture of AlphaGo relied on design principles that were a little bit outdated by the time the AlphaGo paper was published. In particular, the original AlphaGo architecture did not use any residual connections, but by the time AlphaGo was published, the ResNet paper was out. And people came to realize that residual connections were crucial in training image classifiers. So maybe we could use those kind of components, and also batch normalization as well, in the training of these RL agents. Another improvement that could be made is that AlphaGo, the original AlphaGo training, does not use search. So the MCTS search algorithm is employed at inference time only to produce a stronger agent. But what if we can use this stronger agent during training? So these improvements led to the development of the subsequent work AlphaGo Zero. So the original AlphaGo paper used a 13-layer convolutional neural network to construct the policy and value networks. The AlphaGo Zero paper used a 40-layer convolutional neural network with batch norm and residual connections. Also, the policy and the value functions were two heads of the shared base. And since the policy network and the value network perform related functions, you would expect them to utilize similar features. So sharing the base makes a lot of sense when you're training these two neural networks. So a quick takeaway from this is that the way you construct these neural network architecture, it actually does matter a lot. So here's the training pipeline of AlphaGo Zero. And this one is much more simpler compared to the original AlphaGo. So what you do is you perform Monte Carlo tree search using your current policy and your current value network. Recall that the Monte Carlo tree search required a policy and a value function. And then we perform self-play to improve this neural network. And this is a much simpler pipeline. For one reason, rollouts were not used, so the fast policy is not needed. So the algorithm resulting algorithm is referred to as expert iteration. So in step one, what you do is you take the policy, you take the value function, but you don't play directly with this policy. You use Monte Carlo tree search to get this enhanced policy. The actions from the Monte Carlo tree search are stronger than this raw neural network policy. So you have this Monte Carlo tree search enhanced policy, play many games against itself, and that generates an action data set. So given a current state, what action should you take? Well, the good, strong Monte Carlo tree search policy takes a certain action. So that's considered a good action. And then we also have these win-loss data sets. So using this action data set, we train the policy pi, and using the win-loss data set, we train the value function. So let's articulate the key insight of this expert iteration. So given a neural network, you want to improve the policy with neural network plus search, and then train the neural network to mimic this improved policy. So again, this raw neural network policy, you want this to be good, but if you apply MCTS on this policy, you get an even stronger policy. So you have a policy, and there's a way to enhance it. The enhancement is called Monte Carlo tree search. And then you go back and then you ask, well, this policy is weaker than the MCTS enhanced policy. Let me train this policy to match this MCTS enhanced policy. And that improves the raw neural network policy, and that in turn improves the MCTS enhanced policy. So this expert iteration can be thought of as extensions of imitation learning and policy iteration. And this expert iteration learning turns out to be much faster compared to learning via pure reinforcement learning. In terms of performance within the game of Go, the expert iteration of AlphaGo Zero significantly simplifies the approach of AlphaGo, and the result is much stronger policy trained with no human expert data and without any handcrafted human knowledge. So not only is the resulting policy stronger, also the training pipeline is more effective, more efficient. So the expert play data is no longer needed when training AlphaGo Zero. And here we can observe this training plot. So as the training days progress, AlphaGo Zero improves and it continues to improve. It surpasses an earlier version of AlphaGo and another earlier version of AlphaGo effectively. And these earlier versions of AlphaGo did use expert play data, while AlphaGo Zero started from scratch without any expert play data. And in comparison here, the AlphaGo Zero has this much ELO. So ELO is roughly speaking the sort of strength of the agent. And if you compare that with the raw neural network, the raw neural network only achieves about 3,000 ELO. But if you combine this raw neural network with MCTS, then you get this much stronger agent. And the way the expert iteration works is you have the raw neural network try to mimic this much stronger agent as much as possible. And as the raw neural network improves, so does the MCTS enhanced agent. So AlphaGo and AlphaGo Zero dominated the professional human Go players in a spectacular manner. The game of Go was a domain in which people thought that computer agents and AI would never surpass the human experts. But, well, AlphaGo did. And a similar tale of AI beating expert players happened in the domain of poker as well. So here's a sequence of computer poker algorithms. So Cepheus, Libratus, and Pluribus is a sequence of computer poker agents that beat the top human players in different settings. And here's some testimony from the expert poker players. So Jason Les says it's very hopeless. You don't feel like there's anything you can do to win, to beat the computer poker agent. Chris Ferguson says Pluribus is a very hard opponent to play against. It's really hard to pin him down on any kind of hand. Jimmy Chow says, whenever you're playing the bot, I feel like I pick up something new to incorporate into my game. So he's even saying that there's something to learn from the computer poker agent. Okay, so then how did these computer poker bots come to beat the top human players? Well, I won't go into the details as much as I did with AlphaGo, but I'll just say that these poker bots, they do utilize learning, but the capability is primarily due to search. The search methodology that is used for these computer poker bots is quite different from how it's done with the game of Go. It's quite different from MCTS. And in general, how to carry out a search is often domain specific. However, by leveraging search, which is nowadays often referred to as test time compute, one can often achieve capabilities that would otherwise require an exorbitant amount of training time computation. So here is a plot taken from Noam Brown's talk given at the Simons Institute. And on the x-axis, it's basically a number of parameters for these poker bots. And the y-axis corresponds to something like a loss. And as you can see that if you use these trained models and incorporate search, then you achieve a much better performance. Now, without search, if you were to use a pure training-based model or a pure neural network without any search, then it goes down. And you can kind of extrapolate from here and imagine, okay, if the buckets, notice that the x-axis is in log scale, but if you increase the number of buckets and correspondingly increase the number of training compute time, you could extend this plot and it would probably go down and it would probably, go below the level 100 or so. But you can see that if you utilize search, then your plot is at a much lower position. And the amount of extrapolation that you would have to do for this blue line to cross, let's say, this 100 position is going to be exorbitant. So by utilizing some amount of search at inference time, at test time, you're able to dramatically improve the performance and reach a level of performance that probably cannot be reached with any reasonable amount, a practical amount of computation power that's expended at training time. And in fact, we can go back to the game of Go and make an estimation of how much scaling we would need in order to have the raw neural network without any MCTS search to surpass human performance. So this is, again, a screen capture due to Noam Brown's talk given at the Simons Institute. Here is the performance of the full AlphaGo Zero algorithm utilizing Monte Carlo tree search. And this is just the raw neural network that doesn't utilize any search. And the top human performance is somewhere over here. Now, from people's experience, people sort of know that increasing an ELO rating by 120 points requires either 2x, doubling the model size and training, or doubling the amount of test time search. So if you're not going to do test time search and just rely on model size and training, the increase of that, then we can look at the difference here, discrepancy here, and perform an estimation, a back of the envelope calculation to conclude that about 1,000 extra training time compute would be needed. And that's perhaps possible. So compared to the year 2017, when the AlphaGo paper was published, the amount of compute power that these companies have grown exponentially. So maybe if one of these major IT big tech corporations invested all of its compute power on training this Go agent, then maybe the raw neural network might surpass the top human performance. But that would be a mind-bogglingly expensive cost. And also, if you want the raw neural network to surpass the full AlphaGo Zero, the MCTS enhanced Go agent, then you would need to scale the training time compute by 100,000x, and that would just be simply impossible. So in this domain of Go, the best performance is obtained by expending a lot of training time compute and also a lot of test time compute. I want to make a quick remark on why mathematically a test time compute helps. So if you have a pre-trained policy, this is something that must handle all possible game states. It's something that should be able to respond to anything that opponent might do. So finding a perfect policy in training, this amounts to solving the entire game up front. No matter what happens, your policy needs to know what the good action is. In contrast, if you're playing the game and within the game, conditioned on the current game state, if you do a tree search, that tree search only needs to consider game states that can occur given the current state. So some possible configurations that can no longer happen because that's already in the past or certain pieces have been removed, so that cannot happen. Those can all be excluded from the consideration. So in other words, test time compute solves a much smaller subset of the overall game, and it does so only when it becomes necessary. So you look at the current state, and you only need to solve the subset of the overall game that is relevant to the current board state, and that's why test time compute can be much more effective compared to training time compute. All right, so let's conclude. So here are the takeaway from the games. By leveraging test time compute, one can spend extra compute on the given problem instance and deliberate to find good actions that would be otherwise impossible to find using only training time compute. In domains where you have verifiable answers, so in the case of games, you have wins or losses, and these are verifiable in the sense that the rules of the games are explicit. These are you can just write a simple program that can determine whether you've won or lost once you're at the end of the game. So the outcome is verifiable. So in the domains where you have verifiable outcomes, expert iteration can significantly accelerate training compared to pure RL. Okay, so that concludes chapter 1, deep reinforcement learning.